Information geometry gives a way to associate a differential geometric structure to a parametrized family of probability distributions. As suggested by the name, this notion of geometry has roots in information theory and yields surprising insights into many well-known statistical distributions. In this video, I'll discuss some examples of parametrized families whose induced geometry is hyperbolic. This is based off a talk I gave for a probability workshop at the 2022 annual meeting of the Statistical Society of Canada. Since the first talk in the session was an introduction to information geometry, I assumed that the audience was familiar with the basics of the topic, as well as being statisticians. For more background, I'll put some links in the description which cover some fundamentals of information geometry. Most of what I'll talk about are classic results in information geometry, and I'll link to some of the original papers in the description. For a single reference, everything is contained in the paper A Hall of Statistical Mirrors, which is joint work with Jun Zhang. The main focus of that paper is a bit different from this video, and really uses the geometry of exponential families and their inherent duality. As I mentioned in the introduction, information geometry gives a way to study the geometry of parametrized families of probability distributions. In other words, if we have a parametrized family, f of x given theta, where x is a point in the sample space and theta is our parameter, there is an associated parameter space m sub theta, which is known as the statistical manifold. Information geometry allows us to determine the distance between the probability distributions in this parametrized family. We can also calculate other geometric information, such as angles, volumes, curvature, etc., and this will tell us information about our parametrized family. When I first learned this, one question I had is whether it is possible to somehow go backwards and study the distributions in terms of the geometry of the parameter space. In other words, the distributions determine the geometry of the parameter space. Can we go backwards and use the geometry of the parameter space to determine the distributions? After a bit of thought, the answer turns out to be no. For instance, there's no geometric way to distinguish between the parameter space of univariate normal distributions and univariate log normal distributions, because their log partition functions are identical, even though their natural parameters and base measures are different. And just using distances, there's no way to distinguish between any two location scale families, since the Fisher-Rao metric will always induce the same geometry. However, it can be possible to tell them apart if you use the higher order dualistic structure. But these counterexamples are a bit unsatisfying. Log normal and normal distributions are closely related, so it might not be too surprising that they have identical geometries. And location scale families are very similar to each other, so it's not too surprising that we need to consider more subtle geometric invariants in order to distinguish between them. But the answer still turns out to be no, even if we throw away these kind of silly counterexamples. And there's two ways to give this talk. The first way would be what I call the mathematician's way, where I'd write down the associated system of PDEs and discuss characteristics, integrable systems, etc. But I think that's pretty unlikely to be very informative to anyone. Instead, I'm going to take the opposite approach, where I show some important families of distributions which all turn out to have the same geometry, at least locally. In this talk, all the examples will be exponential families with two parameters, and there's a reason for that. It can be difficult to determine whether two abstract spaces have the same geometry, because the statistical manifold is going to be some abstract Riemannian manifold. But there's a relatively simple way to tell whether two surfaces have the same geometry, which is to compute the scalar curvature. when the scalar curvature is the same, the surfaces will be the same, at least in a small neighborhood. So they'll locally look the same, but if you zoom out far enough, you might be able to tell them apart. Okay, let's start with the most basic example. Since this is an audience of statisticians, I'm not going to give a background on the normal distribution. Instead, let me use this example to discuss the Fisher metric, which is one of the central objects in information geometry. The Fisher metric is defined for any parametrized families, and it's given by this expression where we take the derivatives with respect to the parameters and then integrate over the sample space. For reasonable parametrized families, the quantity G will be a positive definite matrix, which depends smoothly on the parameters. In other words, it is a Riemannian metric. In differential geometry, a Riemannian metric can be used to compute distances, angles, volumes, curvature, etc. The details of how we do this are not important for the talk, but intuitively, the Riemannian metric determines the shape of a space. Now, if we do this calculation for the space of normal distributions, so we take this PDF and we put it into that integral, after an exercise in Gaussian kernels, we find the following formula. For those of you who have taken a course in non-Euclidean geometry, this expression might be familiar. It's the Poincare half-plane model for hyperbolic space. Ignoring that factor of 2, which can be eliminated by rescaling the variance. Intuitively, changing the mean and the variance affect the distribution much more drastically when the variance is small. And this phenomena induces the normal family with hyperbolic geometry. There's so much more that can be said about normal distributions, and their geometry has connections to analytic number theory and even the Ricci flow. All of this can be found in the paper I mentioned at the beginning of the talk. In any case, the normal family has hyperbolic geometry. Let's find some other exponential families with hyperbolic geometry. The negative multinomial distribution arises from taking independent draws from a multinomial distribution where one of the events is considered a failure event. For instance, if I roll a dice repeatedly until a 1 comes up, the number of rolls of 2 through 6 before the first 1 follows a negative multinomial, which in this case is a negative sextinomial. This gives a discrete distribution which has the following probability mass function. We can slightly modify this PMF to allow for some fixed number of failures, but for simplicity, let's just consider one failure event. Here, there are n-1 parameters, which correspond to the probabilities of the success events. To simplify, but not oversimplify the geometry, let us specialize to the negative trinomial distribution, where there are 2 success events and 1 failure event. This gives a 2-dimensional parametrized family. In order to understand the geometry of this family, it's helpful to reparametrize the distribution. From a geometric perspective, reparametrizations correspond to changing the coordinates of the statistical manifold, which doesn't affect the geometry at all. It's possible to rewrite this as an exponential family, but for this lecture, we'll actually take the square roots of the success probabilities. When we do that, we can calculate the Fisher metric the same way we did for the normal family, and doing so, we get the following. Again, this is a metric which you might be familiar with if you've studied non-Euclidean geometry. It's the Klein disk model for hyperbolic space. Intuitively, changing the success probabilities P1 and P2 affects the distribution drastically when the probability of failure is very small, because there will be many more draws before you see a failure. On the other hand, when the failure probability is large, changing the success probabilities has comparatively little effect. And this effect induces the parameter space with hyperbolic geometry. There's one more thing to note here, which is, unlike with the normal family, we do not recover the entire hyperbolic plane. Instead, we need to restrict ourselves to the set where S1 and S2 are positive, which leaves a quarter of hyperbolic space. The boundary corresponds to the set where the failure probability is 1. Okay, there's a minor diversion that I have to make here because it's too interesting to go unmentioned. As I mentioned a few minutes ago, there are mathematical reasons why we expect to find many exponential families whose Fisher metric is hyperbolic. And so these two examples shouldn't be too terribly surprising. However, there's another and much more subtle connection between these families. For any exponential family, it's possible to build a pair of Kähler manifolds on the tangent bundle of the parameter space. This duality is closely related to a concept known as mirror symmetry in algebraic geometry, and this notion of statistical mirror symmetry is actually the main focus of our work. These Kähler manifolds detect much more subtle information compared to the Fisher metric alone. However, quite surprisingly, the dual Kähler manifold for the normal family and the primal Kähler manifold for the negative trinomial family have the same geometry, at least locally. In other words, even though these distributions are completely unrelated, these two spaces end up being locally indistinguishable. However, their mirror images are completely different. At least for me, this fact was completely unexpected and something that came as a bit of a surprise. Okay, let's see one more example of a hyperbolic statistical manifold. The inverse Gaussian is another example of an exponential family. As suggested by the name, there is a connection to Gaussian distributions, but it's a bit convoluted. In essence, the idea is that if one starts with Brownian motion with positive drift, the amount of time it takes for the process to reach some positive value alpha is distributed according to an inverse Gaussian distribution. After dimension reduction, there are two parameters, and we can write out the distribution explicitly. What makes this an inverse Gaussian is that for positive time, Brownian motion will be distributed according to a Gaussian distribution. In other words, a Gaussian distribution describes Brownian motion's level at a fixed time, whereas an inverse Gaussian distribution describes the distribution for the time that Brownian motion takes to reach a fixed positive level once you add some positive drift. We can use the same process as before to understand the geometry of the parameter space of inverse Gaussian distributions with parameters mu and lambda. Computing the Fisher metric, we find the following. The scalar curvature of this metric, so we're just going to compute that out, satisfies scalar is identically equal to -1, which means that this is also a hyperbolic metric, albeit its geometry is exactly half of that of the other examples whose scalar curvature was -2. The change of coordinates to relate this geometry to the half-plane model isn't immediately obvious, but was found by Villaroja and Olaire. Doing so, we can see that the parameter space is geometrically equivalent to half of the half-plane. In other words, it's a quarter plane. And so again, like with the negative trinomial distribution, there's a boundary. We don't get the entire hyperbolic half-plane. Let me conclude this video with a probabilistic result which is straightforward to show geometrically, but might be difficult to derive otherwise. The symmetry group of the hyperbolic half-plane is well known and corresponds to Mobius transformations which satisfy AD minus BC is equal to 1. However, most of these transformations will not fix the line x equals 0, which we need in order to obtain a symmetry of the inverse Gaussian family. However, if we scale the half-plane, this fixes the line and preserves the hyperbolic metric. The fact that scaling generates a symmetry has a natural interpretation as it corresponds to scaling the drift nu and the level alpha for the original stochastic process. However, until you do this computation, it's not so straightforward to show that the scaling preserves the geometry. It should be noted that there are other symmetries which fix the line x equals 0, which correspond to inversions around circles centered at the origin. I don't have a good statistical explanation for what these transformations correspond to, so I'd be very happy to hear if someone else can explain them. Thanks for watching, and please leave a comment if you have any questions or suggestions for me. If you're interested in seeing more computations involving the Fisher metric, here's a derivation of the sigma-sigma component for normal distributions at a slightly slower pace. This video was funded in part by a collaboration grant from the Simons Foundation.